Hi there, welcome back to Nadz Academy. In our previous episode, we had explored fundamental concepts of communication, combination of data communication, fundamental characteristics, and data communication components. In this episode, we'll resume our journey from previous episode and explore further aspects of computer networking in detail. So let's jump in. Information today comes in different forms, such as text, numbers, images, audio, and video. In data communications, text is represented as a bit patterns, a sequence of bits, zeros or ones. Different sets of bit patterns have been designed to represent text symbols. Each set is called a code, and the process of representing symbols is called coding. Today, the prevalent coding system is called Unicode, which uses 32 bits to represent a symbol or character used in any language in the world. The American Standard Code for Information Interchange, ASCII, developed some decades ago in the United States, now constitutes the first 127 characters in Unicode and is also referred to as a basic Latin. Numbers are also represented by bit patterns. However, a code such as ASCII is not used to represent numbers. The number is directly converted to a binary number to simplify mathematical operations. Images are essentially intricate mosaics of digital building blocks called pixels. Each pixel acts as a miniature dot, and the total number of these dots determines the image resolution. An image with 10,000 pixels offers finer detail and sharper representation compared to one with only 1,000 pixels, but also demands more storage space. Audio refers to the recording or broadcasting of sound or music. Audio is by nature different from text, numbers, or images. It is continuous, not discrete. Even when we use microphone to change voice or music to an electric signal, we create a continuous signal. Video refers to the recording or broadcasting of a picture or movie. Video can neither be produced as a continuous entity or it can be a combination of images, each a discrete entity arranged to convey the idea of motion. Data flow. Communication between two devices can be simplex, half duplex, or full duplex. In simplex mode, the communication is unidirectional, as on one-way street. Only one of the two devices on a link can transmit, the other can only receive. Keyboards and traditional monitors are examples of simplex devices. The keyboard can only introduce input, and the monitor can only accept output. The simplex mode can use the entire capacity of the channel to send data in one direction. In half-duplex mode, each station can both transmit and receive, but not at the same time. When one device is sending, the other can only receive, and vice versa. The half-duplex mode is like one lane road with traffic allowed in both directions. When cars are traveling in one direction, cars going the other way must wait. In a half-duplex transmission, the entire capacity of channel is taken over by whichever of the two devices is transmitting at the time. Walkie-talkie and radios are both half-duplex systems. The half-duplex mode is used in cases where there is no need for communication in both directions at the same time. The entire capacity of the channel can be utilized for each direction. In full duplex mode, also called duplex, both stations can transmit and receive simultaneously. The full duplex mode is like a two-way street with traffic flowing in both directions at the same time. In full duplex mode, signals going in one direction share the capacity of the link with signals going in the other direction. This sharing can be occur in two ways. Either the link must contain two physical separate transmission paths, one for sending and other for receiving, or the capacity of the channel is divided between signals traveling in both directions. One common example of full duplex communication is the telephone network. When two people are communicating by a telephone line, both can talk and listen at the same time. The full duplex mode is used when communication in both directions is required all the time. The capacity of the channel, however, must be divided between the two directions. Networks. A network is an intricate web of interconnected devices, each capable of communicating with one another. These devices, also known as nodes, can be hosts like computers, smartphones, or security systems responsible for generating and consuming data, or they can be connected devices like routers, switches, or modems, facilitating communication between hosts or bridging connections to other networks. The physical pathway linking these nodes come in both wired or wireless forms, from fiber optic cables to the invisible waves of Wi-Fi. In its simplest form, even your home setup with two computers and plug-and-play routers exemplifies this fundamental principle. A miniature network where devices talk to each other through a connecting magic of the router. Networking criteria. A network must be able to meet a certain number of criteria. The most important of these: performance, reliability, and security. Performance can be measured in many ways, including transmit time and response time. Transmit time is the amount of time required for a message to travel from one device to another. Response time is the elapsed time between an inquiry and a response. The performance of a network depends on a number of factors, including the number of users, the type of transmission medium, the capabilities of the connected hardware, and the efficiency of the software. The performance is often evaluated by two networking metrics: throughput and delay. When we often need more throughput and less delay, however, these two criteria are often contradictory. If we try to send more data to the network, we may increase throughput, but we increase the delay because of the traffic congestion in the network. In addition to accuracy of delivery, network reliability is measured by the frequency of failure, the time it takes to link recovery from the failure, and the network's robustness in a catastrophe. Network security issues include protecting data from unauthorized access, protecting data from damage and development, and implementing policies and procedures for recovery from breaches and data losses. Physical structure, types of connections. A network is two or more devices connected through links. A link is a communications pathway that transfers data from one device to another. For visualization purposes, it is simplest to imagine any link as a line drawn between 2 points. For communication to occur, two devices must be connected in some way to the same link at the same time. There are two possible types of connections: point-to-point and multi-point. A point-to-point connection provides a dedicated link between two devices. The entire capacity of the link is reserved for transmission between those two devices. Most point-to-point connections use an actual length of wire or cable to connect the two ends, but other options, such as microwave or satellite links, are also possible. When we change television channels by infrared remote control, We are establishing a point to point connection between the remote control and the television's control system. Multi-point A multi-point, also called multi-drop connection, is one in which more than two specific devices share a single link. In a multi-point environment, the capacity of the channel is shared, either spatially or temporarily. If several devices can use the link simultaneously, it is a specially shared connection. If users must take turns, it is a time-shared connection. Network topology. The term physical topology refers to the way in which a network is laid out physically. Two or more devices connect to a link. Two or more links form a topology. The topology of a network is geometric representation of the relationship of all the links and linking devices to one another, usually called nodes. There are four basic topologies possible: mesh topology, star topology, bus topology, and ring topology. In a mesh topology, every device has dedicated point-to-point link to every other device. The term dedicated means that the link carries traffic only between the two devices it connects. To find the number of physical links or connections in a fully connected mesh network with n nodes, we first consider that each node must be connected to every other node. We need n is to 1 physical links. However, if each physical link allows communication in both directions, that is duplex mode, we can divide the number of links by 2. In other words, we can say that in a mesh topology, we need n is to 1 by 2 duplex mode links. To accommodate that many links, every device on the network must have n is to 1 I/O ports to be connected to the other n is to 1 stations. A mesh offers several advantages over other network topologies. The use of dedicated link guarantees that each connection can carry its own data load, thus eliminating the traffic problems that can occur when links must be shared by multiple devices. Second, a mesh topology is robust. If one link becomes unusable, it does not damage the entire system. Third, there is the advantage of privacy or security. When message travels along a dedicated line, only the intended recipient sees it. Physical boundaries prevent other users from gaining access to messages. Finally, point to point links make fault identification and fault isolation easy. Traffic can be routed to avoid links with suspected problems. This facility enables the network manager to discover the precise location of the fault and aids in finding its cause and solution. The main disadvantages of the mesh are related to the amount of cabling and the number of I/O ports required, because every device must be connected to every other device. Installation and reconnection are difficult. Second, the sheer bulk of wiring can be greater than the available space can accommodate. Finally, the hardware required to connect each link, that is, I/O ports or cables, can be expensive. For these reasons, a mesh topology is usually implemented in a limited fashion. For example, as a backbone connecting the main computers of a hybrid network that can include several other topologies. One practical example of a mesh topology is the connection of telephone regional offices, in which each regional office needs to be connected to every other regional office. Star topology. In star topology, each device has a dedicated point to point link only to a central controller, usually called a hub. The devices are not directly linked to one another. Unlike a mesh topology, a star topology does not allow direct traffic between devices. The controller acts as an exchange. If one device wants to send data to another, it sends the data to controller, which then relays the data to other connected device. A star topology is less expensive than a mesh topology. In a star, each device needs only one link and one I/O port to connect it to any number of others. This factor also makes it easy to install and reconfigure. Far less cabling needs to be housed, and additions, moves, and deletions involve only one connection between that device and the hub. Other advantages include robustness. If one link fails, only that link is affected. All other links remains active. This factor also lends itself to easy fault identification and fault isolation. As long as the hub is working, it can be used to monitor link problems and bypass defective links. One big disadvantage of a star topology is the dependency of the whole topology on one single point, the hub. If the hub goes down, the whole system is dead. Although a star topology requires far less cabling than a mesh, each node must be linked to a central hub. For this reason, often more cabling is required in a star than in some other topologies, such as a ring or bus. High-speed lanes often use a star topology with a central hub. Bus topology. The preceding examples of all describe point-to-point connections. A bus topology, on the other hand, is multi-point. One long cable acts as a backbone to link all devices in a network. Nodes are connected to the bus cable by drop lines and taps. A drop line is a connection running between device and the main cable. A tap is a connector that connects the main cable to create contact with the metallic core. As a signal travels along the backbone, some of its energy is transformed into heat. Therefore, it becomes weaker and weaker as it travels farther and farther. For this reason, there is a limit on numbers of taps a bus can support on the distance between those taps. Advantages of the bus topology include ease of installation. Backbone cable can be laid along the most efficient paths, then connected to the nodes by drop lines of various lengths. In this way, a bus uses less cabling than mesh or star topologies. In a star, for example, four network devices in the same room require four lengths of cable reaching all the way to hub. In a bus, this redundancy is eliminated. Only the backbone cable stretches through the entire facility. Each drop line has to reach only as far as the nearest point on the backbone. Disadvantages include difficult reconnection and fault isolation. A bus is usually designed to be optimally efficient at installation. It can therefore be difficult to add new devices. Signal reflection at the taps can cause degradation in quality. This degradation can be controlled by limiting the number and spaces of devices connected to a given length of cable. Adding new devices may therefore require modification or replacement of the backbone. In addition, a fault or break in the bus cable stops all transmission, even between devices on the same side of the problem. The damaged area reflects signals back in the direction of origin, creating noise in the both directions. Bus topology was one of the first topologies used in the design of early local area networks. Traditional Ethernet LANs can use as a bus topology, but they are less popular now for reasons. Ring topology. In ring topology, each device has a dedicated point-to-point connection with only the two devices on either side of it. A signal is passed along the ring in one direction from device to device until it reaches its destination. Each device in the ring incorporates a repeater. When a device receives a signal intended for another device, its repeater regenerates the bits and passes them along. A ring is relatively easy to install and reconfigure. Each device is linked to only its immediate neighbor, either physically or logically. To add or delete a device requires changing only two connections. The only constraints are media and traffic considerations, maximum ring length, and number of devices. In addition, fault isolation is simplified. Generally, in a ring, signal is circulating all the times. If one device does not receive a signal within a specified period, it can issue an alarm. The alarm alerts the network operator to the problem and its location. However, unidirectional traffic can be disadvantaged. In a ring topology, a break in the ring, such as a disabled station, can disable the entire network. This weakness can be solved by using a dual ring or switch cabling or closing off the break. Today, the need for high-speed LAN has made this topology less popular. So, as we wrap up, in this episode, we have explored the fundamental characteristics and components of data communications, data representation, and types of data flow, network and its criteria, types of connection, and basic topologies of network. We hope you like this video. Don't forget to like, share, and subscribe for more content. If you want us to cover any specific topic, then let us know by dropping us a comment below. Thank you for watching.